All right, welcome back, and this is our last problem for this topic on torsional members. And this problem, as I have promised, that this is going to be an indeterminate problems. And when we say indeterminate problems, then we need additional equations from the geometry of deformations. Okay, so this problem is taken from the textbook by Beer and Johnston. This is example 3.05. And it says here, a steel shaft and an aluminum tube are connected to a fixed support and to a rigid disc as shown. So here's the setup. We have a steel shaft inside and an aluminum hollow shaft in the outside. And right here, there's going to be a fixed support, and here at this end it should be, or it must have a rigid disc, so something like this. But right here in the figure it's not shown. This is simply for clarity. Okay, so that's our setup. And it says here, knowing that the initial stresses are 0, determine the maximum torque T that can be applied to the disc if the allowable stresses are 120 megapascals in steels and steel shaft and 70 megapascals in the aluminum tube, and use a modulus of rigidity of 77 gigapascals for steel and a 27 gigapascals modulus of rigidity for aluminum. Okay, so here's our problem, and this in terms of cross section we have this, and right here the diameter of this steel tube, because that's the inside material, so the diameter of this steel tube is 50 mm. Right here, that's 50 mm, and for the aluminum tube, this is 76 mm. That's the diameter. And the thickness right here, the thickness of this aluminum tube is 8 mm. The total length, that's 500 mm. Okay, so we are asked to find the torque right here, the torque in this rigid disc, because they are both connected. I mean, the aluminum tube and the steel shaft, they are connected together. So if I twist the rigid disc, then of course they are going to twist together. I mean, they will have the same angle of twist. If you recall that in our lecture handouts about the geometry of deformations, because they are coaxial, so they are going to twist the same amount. However, in terms of torque, they're not going to be the same, simply because they have different values for modulus of rigidity, and they have different diameters and cross-sectional properties. So we expect a different value of torques, right? So there's gonna be torque number 1 for the aluminum and torque number 2 for the steel, and that's gonna be the total torque that we need in this problem. Okay, so let us draw first. Right, so let us draw first. First, the materials individually. Okay, so let's draw the aluminum tube. And right here, let us draw the steel shaft. So this one is steel shaft. let me shade this this cross-sectional area. Okay, so right here we have a diameter of, or I think let's just draw it here. So right here, this is 76. This is 76 millimeter, and we are given this 8 mm thickness. So 76 minus 8 minus 8, that's gonna be 60 mm in diameter. And for this one, this is just simply 50. So this is 50 mm. Okay, so let's write here, this is steel, and the modulus of rigidity is 77 gigapascals. And this one is aluminum, and the modulus of rigidity is 27 gigapascal, sorry. This is gigapascals. And there's also an allowable stress. Right, so for steel, we have an allowable stress of 120 megapascal. So let's write the allowable. And for aluminum, the allowable is 70 megapascals. Okay, and also for the length, this is 500 mm. Okay, so that's our illustration, and we also need to draw. We need to draw the geometry of deformation. Okay, so if this is our cross section, and let's say this is our steel. And the outside, this is the aluminum. So what that means is that if this is our point, initial point, and then if we apply torque, then there's going to be angle of twist. And this angle of twist is, let's say this is our material number 1, and this is our material number 2. So that means that the angle of twist right here, since they are coaxial members, then that means that the angle of twist at 1 is just equal to angle of twist at 2. Okay, so I think we are good to go, and let's solve first for the polar moment of inertia. Because we need we are going to need this parameter, polar moment of inertia, J. Okay, so for J1, that's gonna be the aluminum. So J1 is just by the way, for J1, you would notice that this is a hollow section, so the polar moment of inertia is, the equation is this one. Right, so pi over 32 times the outside diameter, this is 76 to the 4th. This is in mm, minus 60 to the 4th. So what we get here is 2.003 times 10 to the 6 mm to the 4th. Right, so that's gonna be our aluminum, the polar moment of polar moment of inertia of aluminum. And for steel, let's just write here aluminum, and this is steel. And for steel, you would notice that this is a solid shaft, So this is pi over 32 times the diameter to the fourth. So pi over 32 times the diameter right here. This is 50. So times 50 to the fourth, and this is 6.13 times 10 to the 5 mm to the fourth. Right. So now let's use, or rather let's just say use, the geometry of deformation to solve for relationships between T1 and T2. Okay, so I think we forgot to write it here. Let's write, or let's draw here. We need a torque right here. We need a torque of, we don't know that value, so let's just say this is T1, and we need another torque right here. This is T sub 2. Okay, and the reason is that we are asked to find for the torque in this rigid disc. So this torque right here, it's just like let's just write here the right. So this is 0 because we have already written the 1. So let's write or draw the equilibrium equation. Equilibrium, so this is 1L, only equilibrium equation for the rigid disc. Okay, so for the rigid disc, this is it. Right, and right here is our shaft, for example. So I'm drawing this in an exploded view. So right here, if we apply a torque, so if I apply a torque right here, then there's gonna be a reaction. I mean, if I cut a section right here, there's gonna be a torque as well right here, right? So that torque, that total torque, that's gonna be the torque in this aluminum and the torque in the steel, right? So let's write, this is T sub 1, this is T sub 2, and that's gonna be the I mean, the equation right here should be T, let's say this is T0, because that's the total torque. So T0 is equal to T sub 1 plus T sub 2, right? So that's gonna be our basis. And recall that, as I've said, that it's going to have different torques because the geometry is different, the material is different, we have different modulus of rigidity. So basically that's, I mean, the torque would be different. Okay, so going back to our to this step, so let's use the geometry of deformation to solve for the relationship between T sub 1 and T sub 2. Okay, and recall that our compatibility equation, this is just the angle of twist at 1 is just equal to the angle of twist at 2, and the equation for this is just T1 L1 all over JG. Okay, so it's important to write the subscript because this is for aluminum, and this one is for steel. Okay, so T sub 2, L sub 2, J sub 2, and G sub 2. Except that for the length, they have the same length, so we can just cancel that out. And we don't have this value. We don't have the T1, we don't have the T2, but we have the polar moment of inertia and the modulus of rigidity. And so basically, we can obtain a relationship between T1 and T2. Okay, so what is J1? It's 2.003. So 2.003 times 10 to the 6, and this is mm to the fourth, right, times the modulus of rigidity of aluminum. This is 27, and I would like to write in terms of megapascals. So that's 27,000. And for steel, this is 6.13 times 10 to the 5. So here it is. And that's in mm to the fourth as well, right, times the modulus of rigidity, which is 77,000 megapascals. Okay, so if you do the math right here, what you get is a relationship of T1 is equal to 1.146 T sub 2. Right, so that's gonna be our relationship between T1 and T sub 2. Now the game plan is that we don't know which one will govern, because if we say we are going to solve for the torque using the stress equation, let's just write it here. So the game plan is that we have this stress equation, the shear stress is equal to TR all over J, right? And we are going to solve for this. However, we don't know which torque governs. Is it the torque? Is it the torque on aluminum, or is it the torque in the steel? Because we also have to check the allowable stresses for aluminum and steel, right? So let's just use, or let's just solve first. Okay, solve for torque. All right, the torques T1 and T2 based on aluminum. Aluminum allowable stress. And the working equation, recall that this is just TR all over J. So T, if this is aluminum, then this will be T1, R1, and J1. Right, so T1 is just equal to the allowable, right here, allowable aluminum, or let's just write A1, right? All right, let me rewrite it. This is TA1, that's allowable for aluminum, times the J. So that's the J1, that's the aluminum all over the radius of the aluminum, right? So what's this allowable stress for aluminum? It says here 70 megapascals. So this is 70 megapascals times the polar moment of inertia of aluminum. This is 2.003 times 10 to the 6, and this is mm to the fourth, divided by the radius. Now what's the radius? What's the maximum radius? That's just 76 divided by 2. Divided by 2, and this is in mm. Okay, so this one will result to 3,690 Newton meters. Okay, so if we base our torque on aluminum allowable stress, then we have to check if we use this equation. I think let's write it here. Solve for T2 using equation. Let's say this is equation number 1. Using equation 1. So recall that T1 is equal to 1.1462 T sub 2, and if we have the value of T sub 1, then therefore T sub 2 is equal to this is 3690, right? 3690 divided by 1.1462, and this is 3 3,220 Newton meter. Okay, so this is our value of the torque for steel, but we have to check. All right, let's write it. But we have to check the actual stresses. Okay, so let's solve for the actual stress, and this is steel. So based on this torque, what's gonna be the actual stress, right? So this is T. T sub 2, this is 3,220 Newton meter, and our R for steel is just simply 50 divided by 2. So this is 50 divided by 2. So let's multiply this times 10 to the 3 so that we get Newton meter. Newton millimeter. Right, divided by the J. So the J for steel is 6.13 times 10 to the 5. 6.13 times 10 to the 5. This is mm to the 4th, and this is equal to 131.3 megapascals. Okay, so we see right here that the actual stress is greater than the allowable stress. Let's write here steel. Okay, why? Because the actual stress is 131.3, so 131.3 megapascals, and this is greater than the allowable stress of 120 megapascals. Right, so that cannot be. So therefore, this is not, or these are not the torque values. All right, so let's solve for torques T1 and T2 based on steel allowable stress, because earlier we based our torque computations, the torque values were based on the aluminum allowable stress, and we found that that exceeded, the actual shear stress for steel exceeded the allowable stress. So let's check if let's check the torque magnitudes or the torque values if we base that on steel allowable stress. Okay, so for T sub 2, so we still use this equation. Shear allowable is equal to T sub 2 times TR all over J, and we are going to solve for T sub 2. So T sub 2 is equal to the allowable shear for steel times the polar moment of inertia divided by the radius. Now for the allowable shear stress, this is just 120 megapascals, and the J, this is 6.13 times 10 to the 5. This is it, 6.13 times 10 to the 5 mm to the 4th, right, divided by the radius. Now the radius of steel is just simply 50 divided by 2, and this is in mm. Okay, so if you do the computation, what you get is a value of 2,942 0.4. This is Newton meter. Right, so here's our value of T sub 2, and therefore using equation 1, we get T1 is equal to 1.1462 T sub 2. Therefore T sub 1 is equal to 3,372 Newton meter. All right, so we have T sub 1, T sub 2. Now let's check this. All right, checking now the value of T sub 1 if it exceeds the allowable stress just for aluminum. Right, so shear actual for aluminum is equal to T1 R1 all over J1, and T1 is 3,372. Right, so 3,372 what's this, Newton, or let's multiply this times 10 to the 3 so that we get Newton millimeter, times the radius of, what's the radius of aluminum? This is 76 divided by 2, and this is in mm, divided by the polar moment of inertia, which is 6.13 times 10 to the 5. So this is 6.13 times 10 to the 5. This is mm to the 4th, and we get a value of 64 megapascal. So we compare this to the allowable. So shear actual is actually less than the shear allowable, and this is aluminum. Okay, why? Because this is 64 megapascals, and the allowable shear stress is 70 megapascals. Right, so 70 megapascals. So therefore the torque for the rigid disc is, right, TO is equal to, from our equilibrium equation, TO is equal to T sub 1 plus T sub 2, and this is T sub 1, this is it, 3372, plus T sub 2 of, what's our T sub 2? 2942.4. 2942.4, and this is equal to 6,314.4 Newton meters. Okay, so that's a lengthy solution, but if we understand the principles, then I think that's the best learning. Okay, so let's review our problem and our solutions. We have this problem, and it's a shaft. Actually, it's composed of two materials that are coaxial. So we have aluminum right here outside and steel inside, and this assembly, they are connected to a rigid disc, and on the other end is a fixed support, and we are asked to find for the torque right here. So if we apply a torque at this rigid disc, and then what's going to be the value of that torque if we have some conditions that let's say we have an allowable shear stress for steel and aluminum. Okay, so first step that should be done must be to draw the equilibrium equations for the rigid disc. So if we apply a torque right here, there's gonna be, actually if we consider just the rigid disc, then there's gonna be a torque on the, acting in the opposite directions. So that's gonna be a torque, let me draw it here. There's gonna be a torque 1 and torque 2, but if you consider this portion, then the direction would be counterclockwise. Okay, and the relationship is just simply the total torque must be equal to the torque torque in the aluminum and torque in the steel. Now the reason why they have different torques is just simply because they have different geometries, they have different polar moment of inertia, and also they have different modulus of rigidity, which is just simply, or something like a measure of resistance. Okay, so um, after that, then we make some more drawings so that we can further visualize, and we draw the materials individually. Okay, so after that, we draw the geometry of deformation, and we obtain these equations, these compatibility conditions, that the angle of twist at material 1 is equal to the angle of twist at material 2. Okay, so after that, we solve for the polar moment of inertia for steel and aluminum, and then we apply the geometry of deformation. I mean the compatibility conditions. We substitute all the values, and we obtain a relationship of the torque one. I mean between torque 1 and torque 2. So we have these relationships. Okay, so because of that, then we can now solve for the torques. Actually, we 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 have computations for torque based on the aluminum allowable stress, and we found out that if we base the torque value on I mean the computations based on aluminum allowable stress, we we will exceed the actual stress right here. We will exceed the actual stress of the steel to the allowable stress of steel, because by computation we obtain 131.3 megapascals, and the allowable is just 120. So that's going to be failure. So therefore, these are not the torque values. So we shifted or we recomputed the torque values, but at this time we based that on the steel allowable stress. So by computations, we found out that the torque values, this will not exceed the actual stresses of the aluminum will not exceed the allowable stresses, because that's 64 is less than 70 megapascals, right? So this will be the correct values for torque. So therefore, the torque for the rigid disc is just simply T sub 1 plus T sub 2, and we obtain this value 6,314.4. All right, so I guess that's enough for this lecture topic on torsional members, and in the next videos we'll talk about flexural members. All right, so see you in the next videos.